Hello Year 12, welcome to the first lesson in applications of differentiation. So today we're going to be looking at tangents and normals. So the equation of the tangent to a curve y equals f of x at a certain point x1, y1 is given by this formula. So we have y minus y1, x minus x1, then the f dash of x1 is just the gradient at that point. So you might be familiar with this formula for finding the equation of any straight line. The m is just the same as the f dash of x1 here. So let's look at an example. Give you a moment to read that. Okay, so we need our x1 and our y1. We've got x1 here, we need to find y1. So I substitute x equals 3 into my equation. Calculate the different terms and I get y equals 5. So I know that the point 3, 5 lies on the curve, and that's where I need to find the tangent. So when I differentiate this, I get this. I need to find the gradient at this point at 3, 5. So I substitute x equals 3 into my gradient function. So when x equals 3, gradient of my graph is 11. So then I use my formula up here, substituting in y1, f dash of x1 and x1. Then I expand the brackets and simplify. On your CAS, you can get it to tell you the equation of the tangent line by using menu, calculus, tangent line. And you have to put in the rule for the function. You don't need the y equals part, and then the x value. You could actually also put the y value in, but most of the time you'll be asked with the x value. And then it gives you just the x expression. So when you're answering a question, find the equation, you would need to remember to write y equals, in this case, 2x minus 8. Okay, pause the video while you have a go at these questions here. Okay, so the tangent to a curve at a point is the straight line that just touches the curve at that point. So here the blue line is my curve, my red line is my tangent. Because these lines are quite thick, it looks like they follow each other for a bit, but we're saying that they're just touching at one point. The normal to a curve at a point is the straight line that is perpendicular to the tangent at that point. So here is my normal, and that's perpendicular to my tangent. There's a relationship between the gradient of the normal and the tangent because they are perpendicular. If the gradient of a tangent is m, then the gradient of the normal is negative 1 over m. Another way you might have heard of this is the product of the gradient of the tangent and the gradient of the normal is negative 1. What that means is that the equation of the normal to a curve at a point x1, y1 is given by this formula, where this is just negative 1 over the gradient of the tangent. Let's have a look at an example. I'll give you a moment to read it. So, same as with the tangent example, I need to have both parts, both coordinates of my point. I've got that x equals 4, so first I need to find y by substituting x equals 4 into this. So I know that I have the point 4, 2 that lies on my curve, and that's where I'm going to be finding the normal. Now, I need to find the gradient of the tangent to the curve at this point, so I differentiate. Remember that this is the same as 8 minus 3x to the power of a half. So when I differentiate, I multiply by a half, and then a half subtract 1 gives me negative a half. The reason I've rewritten this here, this is acceptable as an answer to a question. The reason I've rewritten it is because when I come to substitute in x equals 4, which I'm just about to do, it's much easier for me to think of the square root of 4 rather than 4 to the power of negative half. So at x equals 4, dy by dx equals negative 3 over 4. So that means the gradient of the normal is negative 1 over negative 3 over 4. And obviously that simplifies, that's where the 4 over 3 comes from. Then I've got my 2 was my y value at my point, my 4 is my x value at the point. So again, I can multiply the brackets out, add the 2. That gives me my equation in my y equals mx plus c form. If for whatever reason we don't really like working with fractions, then we can multiply everything by 3, move it all to one side to get this equation. Either are acceptable unless you're specifically asked to give your equation of the line in a particular form. Pause the video now while you have a go at these questions. Now, sometimes some slightly strange things can happen. So let's have a look at the tangent to the curve x to the power of 1/3 at the point where x equals 0. When I differentiate, I get this. When x equals 0, what that gives me is 1/3 times 1 over 0 to the power of 2/3. 0 to the power of anything is still 0. 1 over 0 is undefined. So our derivative isn't defined at x equals 0. Let's have a think about the graph. Here's my graph of f of x equals x to the power of 1/3. My function is continuous at x equals 0. If we consider what happens to our gradient, as I approach 0, both from the positive side and from the negative side, my curve is getting steeper and steeper and steeper until at x equals 0, I have an infinite gradient. Tangent at that point would be a vertical line, so it has a vertical tangent at x equals 0. And the equation of the tangent would be x equals 0. Let's consider this graph, so x to the power of 2 over 3, where x equals 0. So again, the derivative is this, and when I substitute x equals 0 in, I'm going to have the same problem. I'm going to end up with a 1 over 0, which is not defined at x equals 0. Again, let's consider the graph. So here, remember this is called a cusp, this pointy part. That's the part that we're considering. What does the tangent look like there? So our function is continuous at x equals 0, our function is defined there. As x tends to 0 from the positive side, that's what this means here, x tends to 0 from the positive side, my gradient again gets steeper and steeper and steeper and is tending towards infinity. Here, as x approaches 0 from the negative side, my gradient is getting steeper and steeper and steeper and steeper, but it's negative, and so it's tending towards negative infinity. Just noticed this x here should not be a part of the exponent, it should be just like this one above. So at this point, at the cusp of the graph where x equals 0, this graph has a vertical tangent and its equation is x equals 0 as well. Okay, so these are your final questions from this exercise. Have a go at these. Make sure you're marking your work as you go, and if you have any questions, ask your teacher. Thank you.